Good evening, everyone. I'm Carolyn Freund, Dean of the School of Global Policy and Strategy, which is also known here on campus as GPS. Welcome to this evening's event, Climate Solutions for a Sustainable Future. At GPS, we're dedicated to finding solutions to the world's most pressing policy challenges, and global warming is certainly one of them. Food insecurity, poor health outcomes, water scarcity, migration, and economic disruption are just a few of the effects of rising temperatures. This evening's event showcases research from a group of GPS faculty who are working to bring science and policy together to change the current trajectory. So GPS brings interdisciplinary approach to this challenge. We engage scholars from political science, economics, engineering, physical and biological sciences to identify bold, data-driven, scalable solutions for reducing emissions and adjusting to climate change. And this really is an area where interdisciplinary is so important, because you need the economics to know how much it costs. You need the political to know how to get things done. And you need the science to know what's even possible. So bringing them together is so important. Before turning to the speakers, I want to acknowledge that climate change can be a controversial topic. People have different beliefs about the extent to which climate change is the result of human activity. They have different beliefs about the trade-offs between income growth, poverty reduction, and climate action, and about what are the most effective ways to combat climate change. Our goal is to provide research and evidence to enhance understanding and guide policy decisions towards a low carbon future. And I really want to underscore that we are prioritizing facts and evidence to set the direction. And of course, we aim for outcomes that are more equitable for all. With that in mind, I'm excited and honored to introduce you to the GPS scholars whose research goes to the heart of these issues. David Victor is the Peter Cowhey Center. He's the chair at the Peter Cowhey Center on Global Transformation, professor in innovation and public policy at GPS, and co-director of the campus-wide Deep Decarbonization Initiative. His research lies at the intersection of climate change science and policy, and he is a leading voice on how multilateral cooperation on climate change should be organized. As climate change progresses, global food insecurity has increasingly become one of the most widespread and deadly signs of climate and environmental injustice. Working on this topic is Jen Burney, the Marshall Saunders Chancellor's Endowed Professor in Global Climate Policy and Research. Her research examines how to feed growing populations and stabilize the climate at the same time. Finally, Professor Kate Ricke's groundbreaking research explores whether solar geoengineering, and that's a process where sunlight is intentionally reflected to cool rising temperatures, could help avoid the worst consequences of global warming. Kate holds the Edward A. Frieman Endowed Presidential Chair in Climate Sustainability. So I'm going to turn it over from here to David to begin the conversation, and the other speakers will come on as we go. Thank you all for being here.
Excellent. Well, thank you very much, Carolyn. You have 3 scholars tonight talking about the climate issue. We also have a dean who's a leading scholar on the international trade and macroeconomy aspects of the climate issue, and half a dozen other faculty members at GPS who are working on climate. So we're not going to give you the whole picture, because then you will still be sitting here 2 weeks from now. But we're going to give you 3 slices into the challenge here. So I want to talk, each of us are going to talk for 10 minutes. We're going to have a brief fireside chat. There's no fire, but imagine a fire there. We're going to have a brief fireside chat, then some Q&A, and the whole thing will take an hour. I want to talk about where we are in terms of controlling emissions. It doesn't look like it, but we're actually making a lot of progress. You will see in the news over the next few weeks a tremendous amount of discussion about how we're failing. We're failing to keep 1.5 degrees alive. That's the idea that we should stop warming at 1.5 degrees Celsius above pre-industrial levels, widely discussed goal. 2 degrees, it's actually formally in the Paris Agreement, that will not happen. There'll be a lot of discussion about failure, and that's part of an effort to get more action. We need more action. We should have taken this problem seriously earlier. But when you take a step back, that's actually not the right way to measure progress, because those goals were in some sense never really achievable. And they were collective goals that nobody was individually responsible for. And so when you have a collective goal that nobody is individually responsible for, there's a shocker for you, it doesn't actually happen. But the right way to measure progress, I think, is to think about where we were headed before. So here's a slide you're going to see again when Ricke talks later. This is the last IPCC report, the Intergovernmental Panel on Climate Change. I've been very heavily involved with this since the creation of this organization. We won the Nobel Peace Prize, shared it with Al Gore for work on climate science. This slide shows different projections, scenarios out into the future for warming from the last report. 15 years ago, the world was on track for about 5 degrees C of warming above pre-industrial levels. Nobody really knows exactly how much, but that was the trajectory that we were on. Today, the world is on track for about 2.5 degrees C of warming. So we will fail to meet our goals, the widely discussed goals, but 2.5 is not 5. And that's a way to think about progress. It also means that we have to grapple with the reality of 2.5, and actually the rest of the talk after I sit down will be about that. But I think it's important to recognize that we're making progress, and the key to understanding progress is the new theory of change. This is one of these areas where social science research, like here at GPS, has changed the way the world thinks about the problem. The Paris Agreement is framed in part around work we did here and a new way of understanding the role of international cooperation. And that new way is rooted in this marriage that Carolyn talked about between technology and politics. Whenever a new technology comes into service, it starts off in a small market share, and it takes a long time. It's an infant that takes a long time to learn how to walk. Why am I going to focus on technology? Because we will solve the climate problem a little bit from behavioral change and from reduction in demand and other things like that, but a lot from technology that allows us to decouple economic growth and the expansion of human welfare from the harmful emissions that are caused by that. So that decoupling depends on technological change. Quite often in history, when we have big technological changes, we see the pattern of change follows an F-shaped curve. On the left-hand side is a small market share. It takes a long time for the technology to work. Those of you who bought the first electric vehicles a long time ago, there you go. Thank you, sir, for doing that. And all of us should thank you because you helped bring down the cost curve and improve performance, and that was a selfless act. And so we want to thank you for your contributions to the planet. Early pioneers help improve technologies, and it takes a long time for the technology to learn how to walk and to improve. And then it takes off very, very rapidly. And the takeoff process is not just cost and technical performance, it's political. What we do here is we build models, quantitative models, that allow us to study these processes of technological change in the context of political change. And so we can see which groups become politically more powerful as a result of a technology improving, and that then helps improve the political prospects and then therefore the technological prospects for the new technology. This is at the essence of this new theory of change. And the reason it's important is because the way you're going to change the world is we're going to get volunteers, pioneers, small groups of highly motivated firms and governments that are out there taking risks, creating new technologies, learning what's possible, and so on. We used to call those coalitions of the willing. We used that term for the second trip to Iraq. Didn't go so well, so we don't call these coalitions of the willing anymore. But that's the idea, is small groups of highly motivated actors, not global committees. The global committees have a role to play as well, but that's how you create technological change. This is from a slide here, shows that same S-shaped curve, and orients all 10 of the major emitting sectors in the global economy along the S-shaped curve. Where are we in the technological improvement? This was from a study that we wrote in partnership with the British government and was an intellectual roadmap for how the British convened COP26 in Glasgow a few years ago. It was an effort to take this new theory of change out for a drive and show how, in addition to doing global diplomacy, which you'll see on display in the next few weeks, but also to bring together small groups of highly motivated pioneers, governments, and firms to create new facts on the ground. Each technology is in a different place, which tells you have to do different things in different sectors. You need different partners in different sectors. Down here in plastics, cement, steel, shipping, aviation, we do a lot of work on aviation. You need very different strategies because these are early days of figuring out how to fly aircraft that don't cause a lot of CO2 from burning jet fuel, and in particular don't cause a lot of contrails. Contrails have a bigger impact on the climate than CO2 from burning jet fuel. So you need to really have a strategy and run experiments. We're involved in designing some of those experiments. Other sectors, like electric power, much further along. Almost all the progress we're seeing globally right now is from the electric power sector. There's one thing, energy modelers are in the disagreement business. We're focused on things we don't agree with because that's how we advance science. One of the things all of us agree on is that an economy that decarbonizes is an economy that electrifies. And good news, the technologies, notably around renewable power, are really advancing rapidly for electric power. So you have different strategies for different sectors. Let me just illustrate what this means in practice. I'm going to take one sector that's familiar to all of us, which is electric vehicles. One of the big challenges with electric vehicles is when should people charge? In California, which has a solar-dominated grid, you should have people charge in the middle of the day, because that's when we have excess solar power, the lowest marginal emissions. These are data from our actual marginal emissions from the Southern California grid. They're higher at night, which is when natural gas is at the margin. They're lower in the middle of the day, which is when solar is on the margin. Current tariff structure encourages people to charge at night and to charge at home. It's convenient. How great is that? And so on. We're running a whole series of experiments. In fact, those of you who drive electric vehicles and use the UCSD network, I hope you've joined the Triton Chargers. And if you haven't, please join the Triton Chargers. This is the first large-scale set of experiments on humans. We're not cooking into the grid. Experiments on humans to see how people respond to different kinds of informational prompts and cash incentives to charge their cars at different times of the day and so on. It is producing the first gold standard social science around human behavior and charging. And this is an example of what we do. This is joint between GPS and the School of Engineering. It has to be done anchored in engineering. It has to be done anchored in policy sciences, and in particular the design of randomized control trials, which we happen to be particularly good at here at GPS. So this is the new theory of change that is now playing out, and it is changing facts on the ground. It is explaining progress. It's laid out in a bunch of publications. Here's a piece from about a year ago in Foreign Affairs that lays this out, applies this to the diplomacy that you're about to see that's underway. There's another article that's coming out in Foreign Affairs in about 10 days that applies this to finance. How do we mobilize massive trillions of dollars of private finance? There's a book that I had the pleasure of being involved with that lays this out in book form and the implications of this. I want to wrap up by saying a few implications of what I'm talking about here today. One, we have to be careful that we're not too smug. Here in California, almost everyone cares a lot about climate. We have to pay attention. I know when you see a picture of Congress, you don't immediately think about action. We have to think about how are we going to sustain political support for this. I've had the pleasure of being involved for the last 3 years in a big study from the American Academy of Arts and Sciences, a bunch of people here in the community, members, Irwin, sitting up here in the front row as a member of the Academy, that brought together an ideologically diverse group of 31 Americans to say, what is it that we can agree on from the far left to the far right? No climate deniers, but far left to the far right. What can we agree on? And how do we put together and hold together political action on climate change? That's important because the political winds shift. Shocker. And we need to find ways to not just hold it together, but actually sustain action. And one of the ways you see this is by looking at news coverage. How many of you read the New York Times or the LA Times or the Wall Street Journal or the USA Today? Okay, let's just say everybody here. When you read those news sources, you get a picture of coverage on climate change that is highly skewed to the elite newspapers. When you look at the Heartland, this paper is just going into peer review earlier this week, shows that the blue line, coverage of climate change in the elite newspapers. Coverage is going way up. Dropped during the pandemic because people were covering other things. Came back up pretty quickly. The bottom line shows coverage in 25,000 news outlets, mainly state and local newspapers in the Heartland. The Heartland's paying attention a little more to climate change, but they're thinking about climate connected to other kinds of topics, and that's key to building and sustaining political support. I want to just close by saying, We in California are leaders on climate change. There are a lot of leaders in the world on climate change, but leadership by itself doesn't fix the climate problem. It is a global pollutant. On the left-hand side is emissions of the world in 1990, and I'm not putting names of countries on here, I'm putting their political attitudes about climate change. 1/3 of emissions in 1990 came from countries that would end up caring a lot about climate change and have sustained action over time. That green wedge has been shrinking over time because leaders have done leadership. And so the irony in the climate problem is the more you lead, the less directly relevant to the problem you become, because your emissions go down. And so every action as a leader needs to be evaluated through the lens of whether leadership is generating followership. And so far, there's a lot of leadership and not enough followership, not enough attention to doing things that can be replicated more widely, which is why concentrations of carbon dioxide in the atmosphere, our famous Keeling curve from Dave and now Ralph Keeling, continue to rise. The Keeling curve does not know that we've gotten good at going to meetings on climate change. And even though we're making progress, and that's what I'm suggesting today, we're making progress on the climate problem with a new theory of change that is working. There's a lot of climate change built in the system. In fact, this year, we've been above 1.5 for roughly half of the year. So that gives you some sense of that. Again, it's an El Nino year, a little bit of an unusual year, but the built-in warming is massive. And the next two speakers are going to talk about the implications of that. Jen Burney is going to talk about what does this mean for food security. And then Kate Ricke is going to talk about some ideas that are now being taken more seriously because we have to recognize how serious the problem is and how much climate change is really baked into the system. And with that, I want to give the floor to Jen Burney.
Let me just echo the speakers before me. Thanks you all for being here tonight. It's really nice to see you all. So I want to talk about adaptation in a world that is more serious about climate mitigation, and I want to talk about just one piece of that, because there are many ways, of course, that we need to think about adapting to the warming that is already baked into our system. We live in San Diego. Sea level rise is an obvious way in which we're going to have to think about adaptation. But tonight I want to take on food security. That's where my research is, and I think it's both an incredibly pressing problem and one that demonstrates how there are synergies between adaptation and mitigation moving forward. All right. I want to start with this. This is a summary figure from the most recent IPCC report about the impacts of climate change observed in the recent past on agricultural production. And there's a lot in here. This is like a giant summary of a literature review, right? All the studies that had been published to date. But let me draw your eye to the bottom, which is sort of the global total, and over to the right, which is across all crop groups. And what you'll see is a bunch of bold negative signs, for the most part, indicating that there is strong consensus that there's a negative impact of climate changes that have already occurred on agricultural productivity, with the exception of some places in Central Asia. So we're already in a world where climate is making it difficult to produce enough food. And I want to emphasize a point here as we sit here in California, where it's very easy to talk about being a locavore with any product you'd want within 200 miles on any day of the year. But that's not the reality for a lot of the world, right? The world's food is produced on about 600 million farms, most of which are actually family farms based on designations of their own countries. And many of the producers of the world's food are themselves, in fact, food insecure, and that's putting a lot of land pressure on our Earth system, and that's a huge component of emissions today. So thinking about solving the problem of mitigating climate change inherently includes adapting our food system to a warming climate. The other key point right now, and a way in which the system has changed for the worst in the past few years, is that we have seen a reversal of decades of progress against hunger in the world. So this is from an annual report, The State of Food Security and Nutrition in the World, the most recent iteration, and you'll see that leading into sort of the 2010, 2013, we had pretty steady progress in reducing the number of hungry in the world. That stagnated, and in recent years, that has turned back upwards. And it is not just in a subset of countries in the world, it's really ubiquitous, it's everywhere. And it's not just COVID, COVID mattered, but this is a combination of climate, economic conditions, and civil unrest. on top of that, when we think about sort of what's the world safety net for food security looking like, the World Food Program last year had more requisitions out for food aid and more unmet demand for food aid than ever in its existence. So we're really in a new era of food insecurity. And as David said, we're also staring down some amount of baked-in change. Now, a lot of that is still up to us to control on the mitigation end, but we are looking at somewhere, right, between another degree or more of warming, depending on how aggressive we are. And we need to think about what that means for food security. So that's what my research group does here. When we think about these global averages, they actually belie a lot of regional heterogeneity. So, another degree of warming, so say 2 degrees total, for example, actually looks different depending on where in the world you are. So when you think about some of the parameters most relevant for crop production, temperature and soil moisture, the world looks different depending on where you're sitting. And we need to think about adopting our agricultural production systems to a range of changes that are expected to happen. So how do we do that? I'm, again, only gifted 10 minutes tonight, not 2 weeks of your time, but I'll at least try to entice you to come learn more about what we're doing by saying that we've got sort of a 5-pronged approach to this, all right? So the first is that we're working across disciplines to understand the physical and social dimensions of risk. There are a lot of ways in which changing environmental conditions affect crop production. As one example here, we've done most of the work to show that actually air pollution, in addition to carbon dioxide and other warming emissions, the co-emitted pollutants actually damage crops as well. And so there's sort of an added bonus from the reduction in pollution that you'd expect to get from mitigating common greenhouse gas sources. So this is sort of an extra bonus. But we've shown that across the main breadbaskets of the world, nitrogen emissions have a pretty robust negative impact on crop productivity. Similarly, we've shown that emissions in one part of the world, can be connected to damages in agriculture elsewhere in the world. So this was looking again at pollution emissions from different source regions and the impacts on major cereal crops and soybeans elsewhere in the world. So we've done a lot to map and understand many dimensions of risk. This is just one of them. The second thing we've done is really use data and use big data and use novel computational techniques to learn from what has been tried. Because there is no more robust group of experimenters in the world than the world's farmers. They're always trying new things. They're the best scientists out there, and they're the most in touch with what is happening in their conditions. So we're trying to learn from what's been tried and what's being tried all the time. So as one example, we've used satellite data to look at across the spectrum of irrigated and non-irrigated corn in Nebraska. There's a really a nice gradient there, and you can look at what these crops do to learn a little bit about what irrigation does. And what we've learned was something that I think was understood intuitively but hadn't really been described quantitatively before, and that's that irrigation is, of course, alleviating moisture stress in crops, but it's also alleviating heat stress directly in crops, and about 1/3 of the impact is that heat stress. So this is a really effective adaptation strategy that also, potentially could connect to other mitigation efforts. We then took that and scaled it more broadly globally, and we looked at how irrigation affects cropping intensity, the number of cropping cycles that are able to be produced in any given year. This is a really important margin, right? Food is not like t-shirts where you can just sort of crank up the t-shirt factory when you need more. Food is produced in a seasonality with cycles. We saw that the implications of this with the Russian invasion of Ukraine, right, when the Black Sea port infrastructure was completely frozen, and you can't just dial up more wheat, right? We had to wait for the next harvest to come in. So what we saw here, over on the left here, just looking here, you can see this gray curve is what cropping frequency looks like as a function of temperature around the world, where 1 is kind of a local normal. And you can see that as temperature goes up, the ability to grow additional seasons drops off. And that actually results in the middle there in a dramatic reduction in caloric production around the world. So that's translating directly into a loss of nutrition, and then overall total caloric production loss on the end. All right, the third pillar is that we're testing what works on the ground and scaling it up. And David mentioned that our faculty do a lot of randomized controlled trials. We do a lot of field trials around agricultural technology adoption and everything from new seeds to information to ability to connect farmers to markets and other sorts of financial instruments that help them buffer their own risk. And so we're doing things like individual projects. So here's an irrigation project that I ran for many years, and also a sort of water storage in the form of innovative forage project. So really working to try to think about on-farm water management. And then we've also, we run whole portfolios out of GPS, investing in this kind of beginning S-curve work that David mentioned. I'll remind you all that agriculture was in that leftmost bin. So we're really trying to seed an innovation landscape and figure out what works and then scale it up. The fourth thing we do, we're the School of Global Policy and Strategy, right? We think domestically and internationally. So a lot has changed about the world food economy in the time that I've been a faculty member here. Just to draw out one thing, here's a map of agricultural imports and exports. So if you're in red here, you're an importer. If you're in blue, you're an exporter. This is 2004, and you can see that a lot has shifted since then. Over the past 2 decades, by far the most dominant feature that has shifted in the world is that China has become by far the world's largest importer of food, and that has really shifted the climate landscape as a result through demand. All right, the fifth pillar is that we're thinking about not just how things are changing and where risk lies, but what are the institutions that can respond to risk, and how can we design new institutions where they're needed? So when we think about the way that a crop production landscape is changing, I can tell you about temperature, I can tell you about precipitation or soil moisture, but those are kind of aggregate quantities that don't really help us design solutions, right? The way that farmers work and the way that technologies work is to think about what's changing, in what ways, what's predictable, what's not predictable. And we need to think about all those dimensions kind of independently and in concert. So we've done some work, for example, to decompose trends in major crop growing regions into things like, their trends, their seasonality, how much shocks are correlated over space and time, how much they're idiosyncratic, and to think about the types of institutions that are best suited to respond to those and whether or not they're working. So for example, R&D might be the best way to invest in dealing with longer run trends while thinking about water storage or reinsurance or even cash transfers for shocks are more appropriate lenses. So that's a little bit about what we're doing. I'm going to preempt one question that I know will come, which is to say, yes, we do need more food, all right? This is the UN latest projection, and it has global population sort of barely leveling out above 10 billion right at the end of century. And so in a world, right, where hunger is increasing, this is not just a distribution problem. There are lots of demand changes that can be made, but we really do have to figure out how to grow more food. And we need to do it with no emissions. We're not diving into that part today. We let David talk about mitigation, but we are working on also trying to figure out how to do this while reducing the footprint of food on our climate. All right, with that, I'll pass it off to Kate. Thank you very much.
Thank you. Thanks, Jen and David, and thanks again to everyone for being here tonight. It's a pleasure to get to tell you a little bit about, well, this is a little bit of a scary topic, actually. So now that David has told you a little bit about the progress that we're making and the progress we need to make towards reducing the amount of greenhouse gases we're putting into the atmosphere, and Jen has told you a little bit about what we're going to need to do in one area in order to live with the climate change that's coming, I'm going to talk a little bit about a topic that I work on. That the motivating question is really, what if adaptation and mitigation aren't enough? To get started, basically every ton of carbon dioxide harms us. It does damage every ton that goes into the atmosphere. A few years ago, we published a study that produced this map that looked at what the social cost of carbon is for every country in the world. It was a new method of estimating. The social cost of carbon is the economic damage that's caused by a single additional ton that's emitted into the atmosphere today. One thing that we found in this study is that using our method, the social cost of carbon was about 10 times higher than the value that the EPA was using at the time to make decisions about environmental policy. The other thing that we found, though, as you can probably see in the map, is that the country level social cost of carbon, and countries, this is the level of decision making where enforceable climate policies are made, right, at country level. When you look at how the social cost of carbon is distributed around the world, it's heterogeneous. And this is very illustrative to look at social cost of carbon at this level for the first time, because it shows you why it's been so difficult to get collective action on this problem. In truth, at the national level, everyone's interests aren't exactly aligned. Sure, it's costing everyone, but it's difficult to get fast and effective action when not everyone's in agreement about exactly how much action is going to benefit them, right? So really, what I'm going to talk to you about now is about this residual risk that's going to come from the slow action that we've been taking. Now, David already showed this plot earlier, right? And the good news about climate change is that 10 years ago, these very high warming scenarios on this plot with temperature changes up to 5 degrees, they actually seemed pretty plausible. And now we're in this area where with the existing policies that have already been implemented, we're expecting not to get anywhere close to that, right? So some are more in the range of perhaps 3 degrees of warming. Now, with more aggressive actions, we could get even lower than that into something like this green box, right? Under the Paris Climate Agreement, we're trying to get to the bottom of that green box to 1.5 degrees. That's our aspiration, right? The IPCC that David talked about, this group that collects information about the effects of climate change, they like to present information about climate risks in terms of the amount of global warming with these little figures called burning embers that show you with the amount of global warming what the risks associated with a certain sector are. So Jen was just talking about food production, right? This burning ember plot shows you how risk changes with the amount of global warming according to the experts on this topic in the world, right? And what you can see is that purple is very high risk. Then we've got high risk in red and moderate risk in yellow. And we're sort of headed towards a high risk place. And maybe with our best efforts, we can get down into a high risk region, right? If we look at something like mortality and morbidity in Africa from heat, high risk, very high risk now, headed towards high risk instead. But here in North America, we can look at something like viability of tourism or costs and damages expected to infrastructure. We're in a very high risk trajectory, and maybe we're headed towards more moderate risks. Think about something like coral reefs in Australia or sensitive ecosystems in the Arctic. Well, they're kind of looking like toast either way, unfortunately. And honestly, this is really the motivation for what I'm going to talk to you about now, which is this idea of solar geoengineering. Solar geoengineering is something that people are talking about now. It's also sometimes called solar radiation modification. It's the idea of deliberately intervening in the Earth system in order to reflect more sunlight back into space before it can be absorbed and warm up the planet. There's a couple of different ways that people have proposed doing this. The first one, and the most widely discussed, is called stratospheric aerosol injection. And this is a way that we know we could cool down the planet because it's something that happens whenever there's a very large volcanic eruption. So aerosols are these tiny particles, right? And they can reflect sunlight. When there's a really big volcanic eruption, it blasts a bunch of material up into the stratosphere, which is the layer of the atmosphere above where we live. These particles form, they start reflecting sunlight. They sit there in the stratosphere for a year or two. And we have actually been able to observe after these eruptions how the way that the atmosphere is interacting with solar radiation changes. And we've actually been able to observe how the whole planet cools down after these large eruptions. So it's a process that we understand. And some people are talking about, oh, could we reproduce this? Another approach people are talking about is called marine cloud brightening. This is the idea of seeding low-lying marine clouds. It's another approach where we have an analog that we've already been able to observe in order to see sunlight being reflected by a process that already exists, in this case, ship tracks, right? We have been able to observe that when ships emit soot and things into low marine clouds, the clouds over them, they brighten and they reflect more sunlight, right? So there's a couple of approaches that people have in mind that would allow us to potentially do this if we mimicked those processes, right? Almost all the science and research that's been done on solar geoengineering so far, more than 75% of the papers that have been published have been Earth system science, mostly climate modeling papers. And there's some promising findings from this research. Earth system science actually makes solar geoengineering in some ways look like it works a lot better than we thought it would when we first started doing studies like this about 10 years ago. So this is 4 plots from a paper where they did 2 climate modeling simulations, one in which they looked at what the world would look like with 1 degree of warming from carbon dioxide. That's these maps over on the left. On the top we have temperature, on the bottom we have precipitation, and you can see with 1 degree of warming from CO2, quite a bit of change, a lot of warming, especially in the poles. Precipitation change, some places getting wetter, some places getting drier. And then they ran another set of simulations with a climate model where they said, okay, we're keeping this 1 degree of warming from CO2 and we're gonna offset it with 1 degree of cooling by blocking sunlight. And what you can see is that blocking sunlight's not a perfect substitute for removing greenhouse gases from the atmosphere, right? You've got residual climate change, but it does a pretty good job at cooling things down most places in a climate model, and it makes the precipitation changes mostly smaller as well. An important point that all these studies that have been done show though is that solar geoengineering is never a perfect substitute for greenhouse gas emissions reductions. You always have some residual changes in the climate system, and that's because blocking sunlight is different than warming the planet with greenhouse gases. You can never perfectly compensate. Okay. A report that I worked on a few years ago, one thing that we brought up is that the research on solar geoengineering in the area of social sciences impacts assessment is very nascent compared to this physical science work, and that we don't have enough studies to date in order to make good decisions about solar geoengineering. So for example, we haven't really explored the full scenario space that we need to related to solar geoengineering. The climate context for solar geoengineering and how it might get used and how decisions might get made, it's going to depend a lot on the severity of the existing climate impacts, right? A scenario that people have talked a lot using solar geoengineering for is one called peak shaving, where you maybe would use solar geoengineering. You've got a business as usual scenario here where global temperature is going up. You first manage risk with as aggressive cuts to greenhouse gas emissions as you can. Then you would manage risk further by removing CO2 from the atmosphere, hopefully. And then solar radiation management or solar geoengineering would just be used for a foreseeable amount of time in order to get us through the worst part of the climate change impacts, right? This is called a peak shaving scenario. The physical outcomes of doing solar geoengineering in a peak shaving scenario are like what I showed you in those maps. The problem is that the physical outcomes would look very different if solar geoengineering is used in a different way. So for example, another way it could be used as emergency response, right? Instead of cutting emissions, we just use solar geoengineering as a substitute. A world geoengineered like that would look quite different. And it probably wouldn't look smooth like this either, right? This is global temperature. In reality, if there's a true climate emergency and we haven't cut emissions and we decide we need solar geoengineering, we might have a wiggly scenario like this, right? Okay, so political contexts will also matter. There's been very little work on targeted regional deployments. This is one of the things that my group does work on. For example, we know very little about what it would look like if you tried to concentrate geoengineering activities in certain regions. Some studies have had pretty dramatic results. For example, if you geoengineer just in the Arctic, it can shift the tropical precipitation band southward, which would have massive implications in other parts of the world. Some work in my group, we've tried to cool down the Northeast Pacific to see if we could mitigate heat waves in the western US, and it causes heat waves in Europe. Another study that my group did, we tried to cool down the region of the Indian Ocean to reverse a drought in the Sahel region of Africa, and we found that it caused a drought in sub-Saharan East Africa. So we really don't understand much, and we haven't explored the scenario space very much yet. Also largely unknown, the impacts of these types of activities on health, agriculture, economic growth, et cetera. So the last thing I'd like to say is that there are very active international and domestic policy debates around this technology right now, but it's really important to understand that unlike mitigation and adaptation, the policy conversations about solar geoengineering right now are about doing research. So for example, this is a report that was published by the UN Environment Program this year. The main finding is that we need to understand better what the possible consequences would be. We need an international inclusive research and assessment program. Likewise, the White House published a report earlier this year talking about how the US should develop a program of research into this topic that should include other nations as well as the US. Other international governance bodies, for example, this is the Ozone Secretariat, included geoengineering in its report that was released this year because it has implications for the business the Ozone Secretariat does of trying to reverse the or enhance the recovery of the ozone hole. All right. So food for thought, geoengineering is never going to be a substitute for mitigation and adaptation, but it's something that people are talking about and believe we need more research on. All right, thank you. I'll hand it over to David.
A lot of food for thought. I want to just brief fireside chat. I think we have 20, 25 minutes. And so prepare your questions. Let me first ask just a few here. We're in for a huge amount of climate change, Jen. You talked about the necessity to adapt. I can't increase the volume, but they can probably increase the volume. We have a request for volume, maybe wine. Okay. What's working? You talked about irrigation as clearly that's working. Is that the best example? Are there a few things that seem to be working well, a few things that aren't working well?
Yeah, in terms of adaptation, for food security, there are a few things that are working well. There's a lot of really innovative work that I will call crop development in general, and that is everything from conventional breeding, right? So breeding, for example, flood-tolerant rice has been a huge success. everything from conventional breeding to work that colleagues here at UCSD are doing, harnessing plant chemistry to, create deeper root networks. So really thinking about the dimensions in which the environment of growth is changing and helping crops, sort of better access resources in their own growing environments. It's been incredibly
Seems
successful.
like a lot of those options, take irrigation as an example, it seems like a lot of those options benefit bigger farms, more capitalized farms, more specialized farms. Does this increase inequality that's already a big problem in the farming business?
It's a great question. A lot of our work at GPS has been focused in Sub-Saharan Africa and South Asia. I think with that in mind, the idea being that maybe markets and sort of markets for innovation are sort of working in places with wealthier farmers further along in sort of structural transformation. But one of the things that we've seen is that, for example, mobile technology, low-cost information has really leveled the playing field for farmers, family farmers in smaller contexts.
Let me ask you, Kate, about uncertainty. You laid out, I think, what for many people in this audience is kind of like a Dr. Strangelove, but maybe we need to take Dr. Strangelove seriously because of all the climate that's built in. And you also laid out at the very end an agenda for research. Help us understand how much of this research can be done in the lab with computers, doing these experiments where you casually say we cool the Indian Ocean and then these other people fry, and how much of it needs to be done in the field with in situ experiments, deploying things, watching what happens?
Yeah, I think there's two types of, in the physical sciences at least, there are two types of sort of experiments that we need more of, and one is sort of process-based experiments, and the other is sort of climate effects types experiments. In terms of actual research, when it comes to climate effects, we're never going to be able to do anything except for modeling. And that's because if you were to actually test solar geoengineering at a scale where you could detect the climate effects, you really can't call it research anymore. It's really small scale deployment. On the other hand, we need better climate models in order to have confidence in some of these modeling studies. And for that, there are certain types of experiments, such as how, when you put some sort of gas into the stratosphere, does it form particles that are reflective? How big do those particles get? How much do they actually reflect? How long is their lifetime? These things aren't very well represented in our climate models yet, and we probably will need to do real-world experiments in order to find out the information that we need before we could make good decisions about this.
Quick follow-up on that. How worried are you that some people have tried to do really small experiments like this, kilogram scale experiments? Kilogram's not a big, I know we're all used to using pounds. Kilograms basically 2 pounds. Small experiments. And even that has been politically challenging. Are you worried that our incapacity to do even those field experiments is harming our capacity to understand what could really happen here?
I am worried that it's harming our capacity to understand what's really going to happen here, and I'm very worried about our capacity to do good research in a transparent way, because my big concern is that a lot of this experimental research will just be driven underground by the difficulties.
Or overseas to places where the rules may be a little more lax.
So it is a very complicated question, but yeah, I do think this is a big problem.
Let me ask you, Jen, about uncertainty, but in a different way. You laid out all these different experiments that you do and randomized controlled trials and so on, but you said something really interesting when you presented that, which is we need to pay attention to the institutions that do a good job in managing uncertainty. So what are the attributes of those institutions? Are they have lots of scientists? Do they recognize what they don't know? They all have a sign on the door. Like what should we be looking for in the institutions that do a good job in managing these kinds of pervasive uncertainties?
Yeah, when it comes to food security, we think, we need a new institutional landscape. I brought up the example of the World Food Program, which has been incredibly important historically, but is very slow by design and is fundamentally political, right? The way that a requisition works and how long it takes to be met. When we think about what it might take to get a farmer or a farming household through a bad growing season without, degrading their land or deforesting into adjacent native habitat, maybe it's really rapidly targeted unconditional catch transfers that need to happen. And that's a framework that we don't yet have, but we need safety valves in the system, institutions that are nimble and thinking about these different margins in a way that's not just sort of the old aid and trade regime.
Let me ask, by the way, your job now is to ready your questions. So far, your job tonight has been to pay attention. Everyone's done a great job. Congratulations, everyone gets an A. Now your job is to get ready to ask some questions. And so if you have a question, catch my eye. We've got microphones. I'm gonna ask one or two more here. Let me ask you, Kate, about the magic bullet question. Are you worried that the mere thinking and working on the geoengineering problem creates the impression that we've got a magic bullet there or a rabbit in the hat or whatever the metaphor is that somehow gets people less worried about doing what they need to do, which is to cut emissions and prepare for resilience and adaptation?
It's really hard to say because the social processes that would allow you to answer that question in an empirical way are so complex that it's very difficult to model them in a credible way. The empirical work that has been done so far does not support that hypothesis. It doesn't support the idea that when people learn about geoengineering, that makes them want to mitigate less. Actually, most experimental studies have found the opposite effect, that learning about geoengineering makes people more motivated to mitigate. On the other hand, I think it's a credible concern, but the problem is that we need to learn about geoengineering either way, because even if we think it's a bad idea to do it, even if we think it might reduce mitigation efforts to some degree, someone could do it. It's not that expensive. There's no international laws constraining it. Even if there were, if someone's desperate enough because their whole country is starving, it could happen. And if we don't do research, then we don't know how to respond if someone else does it as well. So either way, you need to do research.
Yeah, so let me see if there are questions here. In the very back there, the microphone's going to come over your head. Oh, it's like a baton. There you go.
There we go, thank you.
Tell us who you are, by the way.
My name is Sandy, and I'm an alum at UCSD. When you're talking about geoengineering maybe making it less likely for individuals to change their behavior, but if we look at your first graph, cement, agriculture, transportation that isn't individual are the things that are driving this. So what things can we do to budge that if we're the ones who are doing it already?
Let me begin that answer and then see if others want to say. So the most important thing you could do is go do your own inventory. Figure out where your own individual activities cause emissions, and then what are you going to do about it? Sometimes these emissions are going to be unavoidable. Like for most of us in this room, probably all of us, flying. So you can't bring your own jet fuel, zero carbon jet fuel, to United Airlines and say, put this in your plane and not your fuel. But what you can do is identify your social cost of carbon. That's in effect, Kate's work has been instrumental in this area. That is in effect an indicator of the cost you are imposing on the global economy for your activities, and calculate that amount of money and take that money and make a donation to a place that's helping people deal with the effects of climate change. That's one thing you could do. But I agree with you, most of the actions are in industry and they require policy and collective action, and therefore voting and policy advocacy are very important. Anyone else want to say anything about this? Okay, next to you. So there was another question up here. Okay, so right there, and then after that, 2 rows up, yes.
Okay, thank you, professors. My name is Xin. I'm from GPS, and thank you for Jennifer. And I have a question for you. Since you gave me a lot of thoughts, and one of the slides you mentioned that China is the biggest imported food country. Even though I'm from China, I don't know that. So, so can you give me more specific details about why this happened and what make it change? What changes this phenomenon? I mean, because of the increased population sharply in this very short period of time, or just because the global warming influence, like the scale of the land or
So tell us why China is now a big importer.
Yeah,
thank you.
so some of it is population, and some of it is something that you probably know deeply from your own experience, which is that every square meter of cultivable land is being used to produce food, right? So just a fundamental land constraint, and so China is importing food as a result. In addition, rising incomes, right? We know that diets shift with income away from starchy staples towards proteins, vegetables, et cetera. So a lot of demand, especially for meat, and that has driven, consequently, demand for feed for production of meat. So soybeans from Brazil predominantly now go to China for feed.
Diet's one of those areas where people can make a big impact with individual choices. Just as the microphone comes up to the next questioner, just quickly on this, Jen, there's also presumably a lot of embodied water that basically is being exported from the big exporting countries to China in the form of almonds and soy and so on.
Yeah, it's true. It's interesting. It is true there's a lot of embodied water that moves around the world. When it comes to what you might think of as like environmental gains from trade, the water story is not quite as bad as we fear, in that places that have more water are growing more food, and maybe that's what we want in terms of
Isn't that
meeting
called
those
gains
needs.
from trade?
Yeah, but environmental as opposed to,
Okay, well, that's
economic.
good. It's nice when the theory works out in practice. Next question right here. Tell us who you are.
Hi, my name is Christoph. I have a question for Kate. I'm curious how much room you see in better analysis of past events, eruptions and things, to actually to better the models that you said should be better.
And then Kate, over that.
Right. Yeah, I mean, Mount Pinatubo's eruption was a huge opportunity, and climate scientists set off to exploit it right away, actually, before we were even thinking about geoengineering, because it was a huge perturbation to the Earth system, and it was a huge opportunity to improve climate models. And since people have been thinking more seriously about geoengineering, people have gone back to dig into that data a little bit to see what more we could learn about geoengineering as well. But one thing that people are thinking about is getting ready for the next big volcanic eruption so we can collect even better data with geoengineering questions in mind. But I don't want to say we've used all the Pinatubo data to its max, but people already were eager to use that event to improve climate models before this.
Back in the
problem.
corner there, and then over here in front.
Thank
We're moving
you.
around. So you folks have not been neglected. You're coming over to this side here.
My name is Michael Walsh. So a two-part question. The first part is...
We got a lot of folks. It's just,
Yeah.
Let's do one question.
One question. Okay, so I see a huge part of the solution could be two crops, which can be cash crops, bamboo and hemp, both which have an incredible range of uses, from food to especially construction with bamboo for homes, and sequestering the carbon captured from these crops into usable things like clothing and homes. So I don't hear enough about that.
Okay. And I think in particular, bamboo is looking very promising. Jen, you want to talk about bamboo and hemp opportunities?
Yeah, sure. I think all of this innovation in the materials side of things is really important, and I agree with you. One of the things we do see looming, though, is just everyone assumes their land base is going to do everything. So when you read these NDCs to the commitments that countries have made to the Paris Accord, almost every country thinks that their land base is going to be a carbon sink. They're going to be soaking up carbon. They assume that they're going to be importing food that's grown elsewhere. They assume that they're going to be importing fiber that's grown elsewhere. And so one key priority for global coordination on research is making sure that these assumptions hang together. And so one of the things I worry about with the hemp and bamboo vision is just this worry about competition over land resources.
And I'll say, for all the faults of the Paris system, one of the big benefits is it has elicited a huge amount of information from countries about what they're trying to do, what they think they're going to do. It helps see whether things are add up. And the bamboo example is a great example where the boundaries around a sector could change. Like right now, we're very concerned about steel. How do you decarbonize steel? Very important question. Some steel applications could be replaced by other materials. We're not quite ready to make the Burj Khalifa out of bamboo, but there are a lot of places where you could do things other than steel. Right in the front here.
Hi, I'm Ray Weiss from Scripps, and I know all of you, of course. I have a geoengineering question, I think mainly for Kate. I accept that we probably need geoengineering if we're going to solve this problem. But my question for you has to do with the fact that if you simply alter the radiation balance in the atmosphere by the kinds of mechanisms you described, you don't reduce the CO2, and so you continue to acidify the ocean if you emit CO2. I noticed you had coral reefs on your list. They won't be helped very much except with respect to sea level rise.
Yeah, so help us understand how to think about
And
that.
if I could throw in one other thing.
No, I know the economy is an inflationary time, but we're not in question inflation because I want to just get a couple
Okay,
more questions.
thank you.
Thanks, Ray. Kate?
Well, most of the corals people I know actually are saying that the bleaching is going to kill all the corals before acidification, but it's a really good point. I don't know a single scientist working on geoengineering that doesn't begin every talk they give about it by saying that it's not a substitute for mitigation. The only way that we could ever do solar geoengineering, and I'm actually not convinced that it's going to happen or should happen yet, but the only way it's going to not be a disaster is if we do it also with aggressive mitigation. And that's what we're going to need to reverse ocean acidification. And everyone who ever talks about geoengineering has to keep saying that. It's not a substitute. It's a stopgap at best.
Yeah.
My name is Larry Peranich. I'm with the Citizens Climate Lobby. And just in the last day or two, Presidents Biden and Xi had a meeting, and there was some climate agreements that have gotten a lot of news. And I'm wondering if you, any people on the panel, have had a chance to look at that. And is this a big deal, or is it just a bunch of hot air?
Yeah, so I've been very heavily involved with that and have looked closely at the communique, the Sunnylands communique. I think it's small. It's a small set of steps, but it needs to be understood in the context of a geopolitical relationship that is in bad trouble. And this is not like the Soviet Union, where we could decouple our economies and so on to some degree. These are the largest economies in the world. They're tightly intertwined. Look at the food trade data. Look at innovation. I mean, why are we in the middle of a solar revolution? We're in the middle of a solar revolution because solar is a global technology. The innovation frontier has moved around the world. The frontier in making solar panels is now manufacturing in China. The frontier in making batteries is Korea, but China's not far behind. So we got to use globalization in a smart way. And I think what you're seeing on both sides is an effort to tamp down the nasty where possible and find things to cooperate on. There's a few areas of that agreement which I think are very promising. High on my list is methane. Methane's a very strong greenhouse gas. If you're worried about rates of warming, methane's a big deal. Both countries have committed to do more on methane. They've committed to deploy more renewables and so on. They're going to do that anyway. But the methane stuff's a big deal. There and then here, and then we're going to take one more question over here, and then I'm going to get, at some point I'm going to get the hook, so I'm going to.
Hello. I've read some articles.
Yeah, I need you to tell us who you are.
Oh, Blaise Narcisi, retiree. I've been reading articles where they're working on ways of actually taking the CO2 out of the air. How practical is it? Does it work? And is it practical? Thank you.
Kate, you want to talk about that? The next one's up here.
Sure. This is a huge area of both research and actual development and investment now, actually. Carbon dioxide removal, and there's a huge suite of different proposals of how you could do it. Some of them are already working, and I don't know if they're cost competitive with other types of offsets yet, but they're getting a lot cheaper over time. Other proposals like, fertilizing the ocean, liming the ocean, these are much more far-fetched proposals right now. But I think carbon dioxide removal is absolutely an essential piece of the climate risk management puzzle now, and there's going to be a lot of work, and it's necessary work to do as well, yes.
And let me just add that this is a partial answer to Ray's earlier question about the acidification of the oceans. You reduce carbon dioxide concentrations. We are standing up an initiative joint between GPS and Scripps on how to scale, how quickly do these technologies scale. So look looking at history, how rapidly technologies move down the S-shaped curve, applying that to these technologies, and then quantifying how quickly this could be material. I think this is a great example where, in this case, climate science connects to social science, and you get new insights that are quantitative that can give you some sense of how relevant an option is. Two more questions, and then we're going to have a lovely reception, one here and then one over there, and we'll call it a night. Thank you, sir.
My name's Carl Yekel, and I'm not sure this question is to Professor Victor or to Professor Ricke, but one thing that terrifies me about geoengineering is that if a nation or small group of nations went ahead with it, that other nations or groups of nations might consider it an act of war. And is there any effort to create some global body that could mediate these things or decide these things?
Okay, Kate, you want to talk about this?
Do you want to talk?
Let me offer an answer, and then Kate will tell us why I'm slightly off base. This, in my view, is one of the most important reasons why we have to do research in this area. Because there are scenarios by which a country, or we were co-authors on a paper that used the phrase green finger, a billionaire self-appointed protector of the planet, I wonder who that might be, could spend a lot of money, buy some islands in the Pacific, have airspace, and then go do geoengineering because they think that's the right thing to do. How would we know? How would we know the early signs that that's happening? It's very similar to the nuclear breakout question. Actually, my thinking on this emerged when Tom Schelling was one of my mentors, who was one of the architects of mutual assured destruction theory. He and I and some others were working on this question of how would we know that another country had breakout? Would it be war? What would we do? How could you respond? That's why, in my view, that's one of the most important reasons for doing the research. You happy with that answer?
I am happy with that answer.
Thank you. Last question right here, sir, and then we're going to have a lovely reception.
I'm Ron, I'm alone. My question is about population growth. It seems like the city and regional governments across the country are constantly under pressure for more businesses, more housing, more people, and talk about the impact of more.
Do you want to, Jen, Kate, channel your inner Paul Ehrlich?
Yeah, sure. So, when we look at what are the most empirically robust findings, like of observing our own world over time, there's a few things that stand out. First, what you've noted, that there's this dominant trend towards urbanization, right? As economies mature and agriculture becomes more productive, people move out of agriculture, they move to urban economies, we progress to manufacturing and industry and then services. And so that goes with strong urbanization, and now we have more people living in cities than do in rural areas in the globe, and that's not turning around anytime soon. There's an efficiency to cities, and that's actually also an environmental efficiency to cities. So it's actually a net good that we think about building our cities better. So I think your head is in the right place. The sort of hidden question in there, though, is like, what do we think about resource use of a higher population? And I would say the other thing we know incredibly robustly across space and across time is that the single biggest way to reduce population growth is to make sure people have enough to eat. Right? So we see that when people don't have enough to eat, when there's really high levels of food insecurity, mortality rates are high, and also to compensate, fertility rates are high. As soon as folks have enough to eat and mortality rates drop, within a generation, fertility rates drop. And so this is another way in which the food security question is so tightly coupled to the climate question. So thank you for bringing that up. It's a nice way to end tonight.
Yeah, it's a terrific way to end tonight. Let me just emphasize, I want to say two things to close. First is we have a very deep bench at GPS working on this issue. We have 3 of us up here. There are a lot of other folks working up here. And we have collaborations with Scripps, with engineering, with other places on campus that give this campus an extraordinary bench on an extraordinarily challenging yet important problem. So I want to ask all of you to do 2 things. One is to join me in thanking the panelists up here and Carolyn Freund. And
the staff at GPS.
And the second is to join us, please, in a reception. I see there's wine. I think it's open. And have a lovely evening. Thank you.